All right, can folks online hear me?
Yep, we got you.
It's quiet in class today. Where is everybody? Pretty soon, I'm gonna just be standing here alone, doing the opposite of it'll be a virtual lecture. It's just that I'm going to be here, and you all are going to be virtual.
Like I said on the timetable, like delivered synchronously from Blacksburg.
Yeah. All right. I hope that you're all in Hawaii or something. That's, you know.
You can just tell people to come in person. You know? Think of it silly.
No, I'm too much of a hippie for that. It's fine if you don't want to be in the classroom. You don't have to be in the classroom. All right. So when last we were talking, we were talking about this concept of a direct conversion mixer, and a direct conversion mixer is just a mixer that mixes the signal down to an IF that's equal to 0. So we sometimes call that spectrum that's centered around DC to some frequency as a baseband frequency. And so we go basically directly from IF to baseband. And the challenge with that, with most mixers, is the dominant source of noise in a transistor at low frequency is flicker noise. So I've kind of drawn it here. We have our flicker noise. The flicker noise has the shape of 1 over F. So the noise rolls off as 1 over F until it reaches the thermal noise floor, and then it becomes thermal dominated. And so if you have information around the signal, it's right around DC, it's particularly challenging for these things. So what happened that allowed us to use direct conversion receivers, or direct conversion mixers, I should say? There's a fundamental transformation, and it was that with digital signal processing, we could start doing things like nulling out the information that was right around DC, so you don't send information right around DC, and that means if there's flicker noise there, we're not putting that noise directly on top of usable signal. So most modern signals do something like this. They'll null out the carriers that are right around DC, and we don't send information there. Okay, so ultimately, one of the challenges, though, with the direct conversion mixer is one other challenge is that we also have to reject the LO, because the LO is sitting maybe centered directly on information as well, and we don't want to down convert the LO to baseband. So I have just a basic calculation that you can kind of follow here to figure out what kind of LO leakage rejection your mixer might need. This would be a system level spec that just says, ultimately we're going to mix a signal down to baseband, and how much LO leakage can get through the mixer and allow me to still receive the signal. Almost always this is based upon some specification related to the SNR that's acceptable at the baseband. In this case, what we're asking is what input to the baseband amplifier would cause an ADC that's following the baseband amplifier to become saturated. So that's the specification that we're looking at here. The big thing that we see when we do this derivation, so here we're checking on the phase of the LO, or the impact of the phase of the LO. So if we have an RF signal that's equal to A times cosine omega t, and then we have an LO signal that's equal to some amplitude of the LO that's a constant. The RF signal might have some time varying amplitude because we might have amplitude modulation of the signal. The LO signal typically has a constant amplitude modulation. And we're going to mix these two down to baseband. So our IF frequency is just equal to the integral over the period, over the symbol period of the LO signal times the RF signal, dt. And we can check to see, what happens if the phase is equal to, different values. And so, here just a hypothetical, what happens if the offset phase in the LO is equal to 90 degrees? And if you go through the math, you'll find that the IF frequency would go to, or the IF amplitude would go to 0. If we tried different values of that offset phase here, we would see different values of amplitude. So the phase variation in the LO itself can cause variation in the amplitude with respect to time. Now that's particularly bad because we don't normally have any way to establish the absolute phase of an oscillator. We can lock the phase relative to a reference, and we can keep the phase relatively constant, but we don't have any way to know exactly what the absolute phase is. And so, if we were to just use a normal mixer with a phase that could start off at any particular value, our receiver might not work very well. So how do we fix that? Yeah.
Pilot tone, and then you lock the.
Well, we could calibrate it. So we could do something. So essentially what you're saying is we send a pilot tone in, we try and figure out what the phase is relative to the signal that's incoming, and then we maximize the signal. So like a calibration scheme where we adjust the instantaneous phase of the oscillator until we get a maximum signal, something like that. Yeah, that could work, but that takes some overhead in terms of we have to add some overhead in the signaling in order to be able to do that. We'd have to have a time varying phase. We'd have to add a time varying amplitude in our pilot tone, and then we sweep the phase until we peak that amplitude. That could be a bit of a problem. It could cause a lot of latency. Anything else we could do? It would work. It would work. Quadrature, yeah, that's the key. We're going to add additional circuitry here. So now, if we use a quadrature mixer, each of these individual mixers is going to be sensitive to the relative phase of the incoming signal, but because both of them are ideally subject to the same relative phase of that LO, I'm going to be transferring more energy into one mixer versus the other mixer, and I'll always get a constant amplitude signal out because that offset phase is going to, it'll be acting in one direction on one of the mixers and the other direction on the other mixer. So this is the common way that we fix this quadrature mixer. You can see here each of the phases of the oscillator, there might be, the relative phase of the LOs going into the mixer is fixed at 90 degrees. I do that by adding an explicit 90-degree phase shift in the path of the LO, or more conventionally nowadays, when I make my oscillator, a quadrature oscillator. So an oscillator that outputs 4 phases. And part of the condition of the oscillator that allows it to oscillate in quadrature is that the phases have to be constant relative to one another. So I can either use a fixed phase shifter that's equal to 90 degrees, or I can just make a quadrature oscillator. Most likely that's what I'm going to do. Okay, now the discussion over the last couple of slides primarily had to do with the fact that we had to worry about flicker noise, and we were looking, and when we're talking about flicker noise, we're talking about transistors that have that are DC biased. They have an average current flowing through them. Those are active mixers generally. We can also make what we call voltage commutating mixers or switching mixers. So in the switching mixer, it's exactly what it sounds like. We just have our RF signal moving through a switch that's being switched at the LO frequency. We can make this a balanced mixer like the one that's shown, where we have differential RF signal coming in and we have a differential LO signal that's controlling these two switches to where one path turns on at any given time. We need, for this to work, low loss switches. Luckily in CMOS, we've hopefully, if you get nothing else out of this class, we can make very low loss switches in CMOS. So they're very good for doing things like switching functions. Effectively, what's ultimately happening with this particular cell is that we're multiplying the signal by ±1 back and forth. So it's kind of the same thing as the current commutating mixer that we talked about before, where we controlled the current flowing through the mixers with a commutating function that was a signum. Here we're doing almost the same thing. We're controlling the flow through the circuit with a signum. And that's going to give us our nonlinearity that allows us to have mixing.
Another question.
Yeah.
The switching mixers. In VLSI, they use like a transmission gauge so that if it's like very up high or very down low, that it wouldn't like turn off the transistor. Do they also do that here? Is that not necessarily just biased to RF, so it's not?
So we would either bias the signal so that we didn't have to worry about that. And most of the time, that's what we do. We add some big resistors to put a DC. We might add some DC level here, bias through a big resistor, so that we can set the common mode to make sure that the switch can always turn on and turn off. What I'm about to show you is that, and that's done, but you can also do a complementary switch. The biggest problem with these commutating mixers is when we use the device as an active mixer, we're using it as a current source. And typically what we see when we're using the device that way is it has good isolation. So it typically only works very well in one direction. And that's important because we don't want the signal we don't want the signal that we're trying to cut off to be transparent to the output at any given time. Now, in reality, this is what our switch looks like. So we modeled the MOS switch as when it's on, it looks like the figure on the left. We've got some on resistance between the source and drain of the transistor. And then we've got some parasitic capacitance that goes up to the gate, which is our control signal, and then maybe down to the substrate. Now, when the transistor is off, that small resistance between the source and drain becomes a very big resistance. And ideally, we don't have any connection path between the source and the drain. But in reality, there is this parasitic leakage path that goes through CGSO, CGDO, and can leak through to the output. And so it's hard to make the switch completely isolating to where when we turn it off, we can't see, it's not transparent. And that impacts the linearity of the mixer and also increases the loss of the mixer. So what people have taken to doing is what we've done in the past. We've just added more transistors to the circuit. So we make these ring mixers and essentially we can basically reduce the effect of that feed through on the signal, because we can get it to cancel if we do things correctly with the phasing of the RF and LO signals as they go through. And in fact, more recently, I'll share a paper. What we've done is added more phases. So here we have a 4-phase, we have a 2-phase, 2-path switch. What they've done is they've made it more like 8 phases with multiple paths through the switch. And if you arrange the paths correctly, you can cause harmonics to be canceled or do all kinds of different things. Yeah. And of course, as a last resort, we can do something like if we really want to reduce the feed through, we can try and do things like resonate the gate capacitance in order to keep it from keep the signal from coupling through from one side to the other.
So these in-path mixers, is it true they're pretty much just for receive? Like I haven't seen any for transmit that I can think of, but are there?
Well, I'll no. You can definitely. So if you're talking about the in-path filters, yeah, I've only ever seen those for receive. Although that's not entirely true. No, I've seen them used once or twice for filtering in the transmit path. No, I've seen them used in both. Yeah. Yeah, anymore, I would say most of the CMOS radios that I see nowadays, they use passive mixers. And I won't necessarily say they use in-path unless you define in as 4, which is a quadrature mixer. But there are at least a number of papers from ISSEC where I've seen them using 8-path filters, but I wouldn't say that they're using them as filters. They're using them to do harmonic rejection. So they're just weighting the inputs in a way that causes the, you can design this in such a way that you cause all the signals at a particular harmonic to cancel with one another, just by playing around with cosines and sines and how they multiply together. I'll share a paper that shows a more modern version of this. The last thing that we can look at is this H-bridge mixer. Now, if we look at this thing, it's pretty similar to the ring mixer that we've shown. The only real difference is how the phases of the LO are driven. But when we make this ring mixer, we can see an easy way to make a fully balanced mixer. Here we have fully differential RF, fully differential LO, and we get all of the same benefits of a fully balanced active mixer. Of course, this one is going to have loss. And then you can conceive of making what looks like a current mode mixer where we take, say, a GM stage, like a differential amplifier. We use that to provide some gain. That could be a low noise stage if we wanted to design it like a low noise amplifier. We send the current into this H-bridge style mixer and then have some baseband amplification that follows. Now, the big benefit to this particular circuit is that these transistors are purely commutating switches. They're not subject to any DC biasing. In other words, we're not putting any type of DC current or constant DC current through them, so they have no flicker noise. And then they also have pretty good linearity that's primarily going to be limited by the gain stages that are surrounding the mixer. The mixer itself will have pretty high linearity by itself, just because all we're doing is switching it.
So the no DC current, does that also apply for the voltage mode passive? Right? Because like, I mean, I'm having trouble
Oh,
Like what you just said, does that also apply for our, because we don't have a DC tank?
yeah, anytime that we don't have, anytime that we're not biasing the current to be on and conducting current, we don't have flicker noise. So when we're just using a switch, or when we're using the mixer as a switch, we're not subject to flicker noise. It's a big benefit to passive. Yeah. Now that said, that baseband amplifier definitely has flicker noise, so you're just moving your problem from one amplifier to the, or from the mixer to the baseband amplifier. Okay, so quick look at mixers, and now we're going to look at voltage controlled oscillators for the next little bit. And then we're going to go back and start looking at some more advanced stuff. Well, we'll do one day looking at the full channel antennas, things like that, and then we'll look at more advanced things that people are doing with cool circuits nowadays. All right, so for our VCO, any other questions on mixers while we're... Mixers are easy to make. You just make a very nonlinear circuit and it will mix things.
So you can tune the, it's true you can tune the LO leakage by applying a DC bias to the input. That's because like, is that very common to like tune that DC bias to the input to get rid of your LO leakage?
Yeah, so there are all kinds of things that people do to get rid of the LO leakage. The main thing that causes LO leakage is really parasitics. So a lot of LO leakage is just getting rid of. It's improving your layout, but yeah, you can do things like you can apply. Let's see. I apply a DC bias. Yeah, I mean, you can do things like apply a DC bias to the gate to cancel, or to find an optimum point to operate. Yeah. Okay. Yeah. Mixers, I don't find particularly interesting because they just tend to be very brute force in their design. I don't find them to be very elegant. You can do things like apply DC biases and. What we do, actually, interestingly, one of the transmitters that my group works on a lot, we use mixers. Our mixers are logic gates. We just mix with an AND gate or an OR gate. And I'll show you that in a few days. We'll look at one of the full transmitters that we do, just to see what's different about it compared to these more traditional amplifiers and things like that that we've talked about. Okay, so voltage controlled oscillators, last major component of a radio. Now, obviously, how we put everything together is very important, but you can make a radio pretty much with some type of amplifier, some type of mixer, and some type of LO, whether it's in the transmitting direction or the receiving direction. You're either up converting from low frequency to high frequency, or down converting from high frequency to low frequency. Our voltage controlled oscillator, here's our mathematical model for the oscillator. We have some control voltage and we have some output frequency, and we can conceptualize this with an equation that just says that the output signal from the VCO with respect to time is equal to some amplitude Vm times sine times omega naught of t, and we call this quantity omega naught of t. This is the total phase of the oscillator. Okay, so if we were to plot the phase as a function of time, it's just going to accumulate, and the rate that it accumulates with over time, the slope is going to be equal to the frequency of the oscillator omega naught. If we have two different oscillators, let's say we have two oscillators now, one of them has a signal V1 of t that's equal to Vm times sine of omega 1 of t, and we have a second one that is equal to V2. It's equal to Vm sine of omega 2 of t. And we were to plot the phase with respect to frequency. So this is V2, this is V1. What can we say about the relative frequency of these oscillators? Omega 1 is greater than omega 2. So we accumulate phase faster. That means that our frequency is faster. That's the slope of these two transfer curves. Okay, so V2, oops, I should say V1 accumulates phase faster. Okay, so ultimately what we're saying is that higher frequency equals faster phase accumulation. Okay, now that suggests something about how we can define frequency. So we're going to define frequency as the derivative of phase. Just going along with those two plots that we just made, and we can say then that omega is equal to d phi by dt. And if we were to solve this equation, we'd say that phi is equal to the integral of omega dt, maybe plus some initial conditions. Okay. Now for our VCO, we're going to make another definition about its operation. We're going to say that the output frequency of a VCO is equal to some frequency omega naught. We're going to call that the free running frequency. This is the frequency that the VCO wants to operate at, plus the gain of the VCO. We're going to say that it has a gain that's proportional to some frequency divided by V times some control voltage. So the output frequency of our VCO is equal to the free running frequency plus some control that we're applying to the VCO by adding that control voltage. All right, so we can now figure out what the output voltage of the VCO is by plugging a couple of these things together. So we can say that the output voltage of the VCO is equal to some amplitude times cosine of that instantaneous phase that we found on the prior slide, which is omega integral of omega out dt plus any initial conditions, phi sub 0. And we make a few substitutions here. We find that this is V naught times cosine of omega naught of t plus k VCO times the integral of the control voltage dt plus our initial conditions. And we call this term here the excess phase. So we're going to be accumulating phase at the oscillator's free running frequency at that rate, plus any additional control that we're applying to the VCO through the control voltage. So we can say that the output phase of the VCO with respect to time is equal to k VCO times the integral of the control voltage dt. All right, now we do a Laplace transform on this. What's our Laplace transform? End up equaling phi of s. What's the Laplace transform of an integral? Surely you know that.
1 over s.
Yeah, 1 over s. Integral is 1 over s. Low pass filter. Okay, so now we can write a transfer function, which we'll say is phi out over V control with respect to S is equal to K VCO. Oops, I forgot my V control here. There we go. That looks better. Okay, so our transfer function for the VCO, the phase is the integral of the phase with respect to the output or to the control voltage is equal to the gain integrated. All right, now we can modulate the VCO. So let's say that we made V control time varying. So let's say V control is equal to Vm times cosine of omega m of t, or omega m times t, sorry. So we add some sine wave on the control voltage. And we'll assume that Vm and omega m are small, at least relative to the amplitude of the VCO and the frequency of the VCO. This is just a small modulating tone that we're going to put on top of the VCO. So we go back and substitute that Vm signal in for the control voltage. And we would find that the output voltage with respect to time is equal to E naught cosine of omega naught of t plus k VCO times the integral of Vm cosine omega m of t, or times t dt And if we carry this all out, we'll find that this is approximately equal to V out or V naught cosine of omega naught t plus k VCO omega m over, sorry, k VCO is Vm over omega m times sine of omega m of t, or times t. Okay, this I used. We can use this trigonometric approximation. Cosine a plus b is equal to cos a cos b minus sine a sine b, and ultimately show that this whole thing is approximately equal to v naught cos omega naught t minus k VCO times Vm times V naught over 2 times omega m times the quantity cos omega naught minus omega m times t minus cos omega naught plus omega m times t. Okay, so now if we look at the output of our VCO after we've added this modulating tone on it, what does it look like? Well, we've got our output frequency that happens at a frequency, our output signal that happens, sorry, our VCO frequency that happens at a frequency of omega naught. Then we have these sum and difference terms that modulate the VCO. And they happen at omega naught minus omega m plus n omega naught plus omega m. Okay. Interestingly, I'm working on an atomic clock problem right now where we're actually modulating the sidebands of a VCO in order to stimulate a cesium atom using the relative difference between the upper sideband and lower sideband, doing a trick just like this. All right, so our VCOs are going to be used in a lot of different circuits. The main one that we care about for our radios are frequency synthesizers. So most of the time, the way that we change channels in a radio is by changing the center frequency of oscillation of a VCO nowadays. In wireline transceivers, these are used in clock and data recovery. So if I send information across the wireline bus, I can use a local oscillator to help recover the clock signal so that I don't have to transmit the clock signal. This assumes that the data has a certain amount of periodicity in it. Of course, we can also use it for clock generation and processing. Bedad can tell you all about clock generation. He's had a lot of fun with it. Okay, now in general, when we talk about oscillators or VCOs, there are two types of VCOs. Our first one is called a relaxation oscillator. Okay, now these are characterized by relatively poor phase noise. and high harmonic content. An example is this Bose oscillator that's shown here. We've got a Schmidt trigger with an RC circuit and a constant current source that's feeding the RC circuit. So more or less what happens is that that current source keeps charging up C until it fills up. Since the voltage of the capacitor will go up as we pump charge onto that capacitor, it will get to the point where it causes the Schmidt trigger to reset, or to turn on. It'll reset the whole circuit, when it does that, the output will toggle from high to low or low to high, whichever state it was in the prior state. The way to think about a relaxation oscillator, and these are commonly things that we use for timers. They're not necessarily something that we would use for the LO in a communication system. The analogy to this, why do we call this relaxation? Well, imagine you have a system like this. You got you got some type of balance beam. And at the top of this balance beam, you've got a basin, and you got a tap that's filling this thing with water, just constantly dumping water in. And down at the bottom, you've got some mass. And you can imagine what happens is the water is going to fill up. At some point, it gets heavy enough that the water is heavier than the mass. It tips the weight. All the water sloshes out, and the weight becomes heavier again. And this system just keeps repeating itself. Okay, now you might also imagine why this thing would be noisier than other types of oscillators, at least with respect to phase noise. In the oscillator, phase noise has to do with when if I have a signal, a clock signal. Phase noise is basically measuring the uncertainty of when the edge of the clock arrives. Now we expect when we have a clock signal that the clock always arrives at some predefined period. So 500 nanoseconds or something like that, the clock is always going to be, the edge of the clock will always be at 500 nanoseconds. But due to random fluctuations in the performance of our devices, the connection to the supply, all kinds of things, the edge of the clock is uncertain, and that's called phase noise. Now you can imagine with a system like this, there are all kinds of things that might cause the edge of the clock to be a little bit uncertain. The flow rate of the water has to be very precisely controlled. If it isn't, then that's a problem. Now remember, the water source in this analogy is like our current source in the prior slide. And remember, current sources have random noise. So the rate at which the basin at the top gets filled up, it's going to fluctuate a little bit. That might cause the edge of the clock to be uncertain. There might be some friction in the balance that causes it to operate a little bit inconsistently because even that's going to be subject to some type of mechanical noise. Yeah, all kinds of things can happen. So that's why these things are susceptible to bad phase noise, but useful for timers. They're very useful for timers. That's where primarily you'll see them used. Okay, now our next type of oscillator, and really the one that we're going to spend the most amount of time talking about, is our harmonic oscillator. These you might see called LC oscillators. It's one type. We also have ring oscillators that would show up here. Now, relative to the relaxation oscillators, these have high spectral purity. So less harmonic content, and they have good phase noise. I actually don't know that we talked about phase noise yet, for any reason. Yeah, well, for the time being, just know that when we make an oscillator, let's say that this is our center frequency, we'd ideally like the oscillator, the signal of the oscillator and the frequency domain to look like an impulse, right? But in reality, because of the uncertainty of when the edge crossing happens, the energy is going to be spread out from the center frequency of oscillation, and it'll be modulating the VCO. That's where that omega m shows up. But it's noise, so it's random. So we just have kind of a probability that the signal is going to have a certain amplitude at a certain offset from the VCO. So a real VCO ends up looking like kind of a skirt that goes out.
How wide is the
Depends upon how good the oscillator is. Good oscillators have very narrow skirts. Bad oscillators, it can, they're wide. We measure phase noise in terms of, we call it a dBc per hertz at a particular offset frequency. A good oscillator, or in terms of jitter. So jitter is this timing uncertainty. So the smaller the amount of jitter, the more certain we are when the edge is going to be. Good oscillators nowadays have jitters that can get down into the femtosecond range. Your more poor ring oscillators and things like that will be in the picosecond range. Okay, so let's look at an oscillator model. First, we're going to start with a two-port model. So here is our two-port model for our oscillator. Those of you that have taken analog before might have seen a circuit that looks like this. So we have some transfer function in the forward direction, A of S, and we have a transfer function in the reverse direction. We'll just say it's called F of S. And we connect this with a feedback loop. We might have some input signal X, and we might make this a negative feedback loop. Okay, so if we want to calculate the transfer function for this thing, here's our circuit. What does our transfer function look like for this circuit? First order control loop, right? So it's always the forward gain over 1 minus forward gain times the reverse gain. Okay, now we care the most about this quantity that we're going to call the loop gain. The loop gain is defined as this term A of S times F of S. So this term right here. And we can come up with a stability criterion. So if we wanted to make this thing unstable, what would we want A of S times F of S to be equal to? 1, yeah. If A of S times F of S is equal to 1, the denominator goes to 0, and this transfer function blows up to infinity, right? And indeed, they call that the Barkhausen criteria for oscillation. And we can write this in terms of magnitude and phase. What we're really saying ultimately is that the magnitude of A times the magnitude of F has to be equal to 1, and the phase of A plus the phase of F has to be equal to 180 degrees. And this is assuming negative feedback. If we already had positive feedback, then we would need 0 degrees. Okay, so now this is a condition that we say is necessary for oscillation, but not necessarily sufficient for oscillation. Okay, so let's check out an example of a ring oscillator. All right, so here is our ring oscillator. We're going to try and get really simple here with our ring oscillator. We have an inverter. So the drain voltage of this common source stage is inverted in phase from the gate voltage, right? So if I loop the output back to the input, does this oscillate? So what is the phase shift at DC in this system? So going from gate to drain, what is the phase shift around this loop? Yeah. 180 degrees. It's an inverter. Now, I know I said at DC, there's no phase shift at DC, but at very low frequencies, very close to DC, it's 180 degrees. What phase shift does the RC circuit contribute? Yeah, so at DC, it's pretty close to 0 degrees. And if we go to very, very high frequencies, it goes to 90 degrees, yeah. We're just talking about magnitudes of phase shifts. Of course, that happens at nearly infinite frequency that we actually get to 90 degrees. So what's the total phase shift we have possible around this loop? As I go to higher and higher frequencies, the maximum phase shift I can get is 270 degrees, right? All right, so can we ever get oscillation from this thing? with the negative feedback connection, you know, going around that loop, I'm getting 180 degrees. The RC is giving me another 90. I need to get 0 degrees as I come back to the input. So no. All right, so our simple RC circuit doesn't work for our simple inverter with a feedback loop around it. Does not work. Let's see what happens if we do 2 of these things. All right, what's our DC phase shift? As we traverse the loop, going all the way back.
0 degrees.
I'll say 360, but yeah, could stay 0 degrees if we wanted to.
So, sorry, I don't understand the term ECE. Like,
I just mean, what's the phase shift around the loop at frequencies that are very close to DC? So, yeah. Now, we have 2 poles now. So how much do these give us? 180. Maximum of 180. Yeah. All right. So our total phase shift is now equal to 180 degrees, assuming that we wrap around every 360. Still doesn't oscillate, right? All right, well, 2 analog inverters don't work. What if we took 2 analog inverters and then we added an ideal inverter at the output? And we'll just assume that the signal swing was big enough that it could trip that ideal inverter, no matter what. That's our total DC phase shift. Yeah, 180. We still have the 2 RC poles. We said that that was 180. Of course, this happens at what frequency? Omega going towards infinity. So we get a total phase at very, very high frequencies that's equal to 0 degrees or 360, whatever we want to call it. All right, that's good. So can we oscillate here?
if you're oscillating at infinite frequency.
Even if we were going to infinite frequency, what do you think the amplitude is at infinite frequency?
0.
Yeah, we have 2 poles that are rolling the amplitude off at 20 dBs per decade. So this is also still a problem. It's good though, our phase condition is satisfied. So we're going in the right direction. Like with all analog and RF circuits, adding more transistors brings us closer to a solution that will work.
Is there a component in the PDK for ideal inverter that we can use there?
So, well, I don't know about an ideal inverter. So if you look at my, there's a Walling AHDL lib that's available. That one, I don't know if I have an ideal inverter, but I do have ideal switches that you can make an ideal inverter from.
Yeah, an ideal inverter that you make it layout and super cheap.
Well, if I make an ideal inverter and layout, I'm going to patent it, and it'll be a superconducting inverter. Yeah.
Room temperature inverter.
Yeah, a room temperature superconducting inverter. Yeah. Okay. All right. Well, let's just add a third analog inverter stage here and see what happens. Well, we can quickly surmise that the DC phase shift is equal to 180 degrees. I've got 3 inverters, so 180 plus 180 plus 180 is 540 minus 360, 180. at a frequency of omega is equal to 1 over RC, the phase shift is equal to 135 degrees. At omega is equal to infinity, the phase shift is equal to 270 degrees. So we get 45 degrees at the pole times 3 is 135, or 90 degrees at infinite frequency, which would be 270 for 3 of those. So somewhere between a frequency of omega c and infinity, we can get a phase equal to 180 degrees. And we can presume that if we design this appropriately, we'd have enough amplitude left over that we could satisfy the amplitude criterion and Barkhausen's criteria. So we'll say that this can oscillate. All right, now let's figure out what condition we need. What do those R's and C's need to be equal to in order to make this oscillate? All right, so what's the gain of each stage? So what is I asked you, what is V out over V in as a function of frequency? What do we have here? Yeah, there we go. Minus GM times R over 1 plus SRC. So the gain is equal to GM times R, the low frequency gain is equal to GM times R, and our pole frequency is equal to 1 over RC. So we can rewrite this as V out over V in of S is equal to minus A over 1 plus S omega P. Now our total gain is this cubed, right? We have 3 of these cascaded. Okay. Now, in order for this to oscillate, I need each stage to contribute exactly 60 degrees of phase shift. If I have three stages that are identical and they each contribute 60 degrees, I'll get my 180 degrees. And I already have the minus sign giving me the other 180 degrees. So I'll have oscillation. So I can find that the tan inverse of omega over omega p has to equal to 60. Am I running out of time? Yep. Okay, 10-minute warning. In a basketball game, 30 seconds can last 10 minutes. So, I can only imagine what this feels like for you guys. All right, we can solve this. Omega naught is equal to square root of 3 times omega p. And we can go, and we know that the amplitude condition we need to equal 1, so we can say that the magnitude of the amplitude condition has to equal 1, and ultimately we can solve and show that that means that A has to equal 2. All right, so this is just, of course, substituting S is equal to J omega and finding the magnitude of that transfer function. All right, so we know now to oscillate, omega naught is equal to the square root of 3 times omega p. And A is equal to 2. Those seem like they're pretty doable. Now, in reality, this is a condition that makes it just sufficient to start and sustain an oscillation, or I should say to sustain an oscillation. If you were to set the gain equal to 2 and the pole frequency equal to whatever your desired output frequency is divided by √3, is this going to oscillate? Maybe, maybe not. Yeah. So normally you need to give it a little bit more gain to get it to start an oscillation, and then the oscillator will tend to stabilize itself. Basically you give it conditions that would cause exponential growth in the oscillation, and then once the oscillator reaches a sustained oscillation, it tends to have feedback conditions that cause the gain to drop, and it reaches a steady state where it's exactly meeting the Barkhazen's criteria. So you give it a little bit of extra oomph, it starts up, and then it will drive itself to sustain the oscillation. Most of the time, how do you start an oscillator up?
Attach an antenna to the PCB so that you pull like signals in the environment into the loop.
It's usually good enough just to turn the thing on. The transient will generally kick it over and start it up. Not always. If you designed it well, that's enough. Okay, so let's look at our closed loop transfer function. All right, so I'm just assuming here that f is equal to -1. All right, and we can quickly, right? Something like this for our transfer function, and we can find the poles. And there are going to be how many poles? 3, all right? I got 3. We got a third order in the denominator. So we're going to have a pole at S1 is equal to 1 minus A times omega P. And I've got complex pole S2 and 3 are at -1 plus A times 1 plus or minus the square root, J times square root of 3 over 2 times omega P. And if we set A just greater than 2, we can show that S2 and 3 are in the right half plane. So that's the thing that will cause our oscillation to kick off. It'll cause, it's unstable, right? So it'll cause exponential growth. That exponential growth will self-quench at some point, and move the poles from the right half plane to where they land exactly on the imaginary axis. So our system starts off with, our poles right here, and then as the oscillation builds, the wave will start to saturate. It'll lose some gain because of that saturation effect, and these poles will move to where they land exactly on the imaginary axis, and that is where we sustain oscillation.